This is section 7. We're going to introduce Gauss's law. That's the second half of the unit. This is kind of new to you. It's not probably totally new to you because we did talk about magnetic flux, but electric flux is a little bit different. So some of this is a little bit of review, some of it's not. Okay. Consider a house with two windows. The windows have equal size, but one is on the roof and the other is on a wall as shown. Which window has more light passing through it? Well, if you take a look at these little arrows, these are supposed to represent the sunbeams, and you'll notice that the sunbeams are striking perpendicular to the window on the roof, but then they strike at an angle on the window on the side, right? So this one's getting the full sunlight, and this one's kind of only getting a chunk of it, right? You're only getting some of the sunlight, right? You're not going to get all of it because you're going to miss some that doesn't quite hit the window, but here it's going to get all it possibly can. So the roof window, and the physics explanation for that is because its plane is more normal to the sunbeams. Okay, and by normal I mean perpendicular. Okay, you might have heard me say that a couple times, but normal is the same thing as perpendicular. Okay. Flux, we learned with magnetic flux, is like when the magnetic field lines pass through a surface. It's the same thing. It's a quantity that is flowing through a surface. Okay? And in this case, it's electricity or electric field. Okay? From the example of the sunlight in the house, what three things affect how much light passes through the window? If we were to wanted to change the amount of light that passes through the window, there's three main things that we can do. Three big things we can do. First off, we can change the window's orientation, okay, relative to the sunbeams. Okay. We can change the area of the windows. So we can make them larger or smaller. And then we can also, this is going to be really hard to do, but we can change the brightness of sunlight. Okay? Think of the sun as like a charge. Okay? And think of the windows as windows. Okay? You know, if we make the sun stronger, we give it more charge, so to speak, then it can emit stronger amounts of light, and then we can get more light to go through the house, right? Okay, Gauss's law deals with the flux of electric field rather than light energy or water flow. We have to define something called an area vector. Okay, area vector is a vector that points perpendicular to the surface. Okay, the area, right? So it points perpendicular to the surface and it points out. So we've got like our area vector right here. Our area vector is at an angle now because we've tilted the shape, and then now it's going straight up. Okay. Electric flux is to find the greatest amount of electric flux, we need to look at how much of the surface area is being exposed to or how much of the area is being exposed to the electric field. So we got an E field turned on here, and we've got our shapes in there. This shape is getting exposed to the most electric field because you'll notice it's got, all of this, all of this at the front is being exposed to it. And another way to think of it is the area vector is parallel to the E field. Okay. Here, we're going to have not as much flux going through it. Okay. You can see that even though we've only got 3 lines here going through it, okay, and 3 lines here going through it, you'll notice that there's this little gap right here, okay, that now the flux is not flowing through. Okay. In diagram 1, it is flowing through right there and there, right? But in diagram 2, the flux is not touching those areas. It's not as there's not as much flux flowing through, or not as much E field flowing through the object. In 3, you're going to see that very little E field is flowing through the object, right? You've got this very, very little, this piece is getting E field through it, and then all this missing part up here is not getting any field. So 1 is going to have the most flux through it, and 3 is going to have the least flux because you'll notice that there is less E field flowing through the surface in 2 and 3 than there are in 1, and less in 3 than there is in 2. Okay. Basic equation for electric flux. This is on your formula sheet. It is this right here is phi equals E A cosine theta. Okay. Um, E is obviously the E field. A is the area vector. Okay. Or the area that flux flows through. Is most typically a surface area. Okay. And then your theta is the angle between the E field vector and the A area vector. Okay. In general, the short form of this equation is expressed as a dot product, okay, E dot A. Okay. That's the short form of it when it's expressed as a dot product of two vectors, because these are both vectors, right? So E field and the area vector. Okay. The sign on flux can tell you which direction the flow is. So, for example, if you have a positive flux, okay, then that means that E field flows out of surface. Okay. And if you have a negative flux, then that means that the E field flows into surface. Okay. So if you ever see positive flux, just know that that means that there's E field flowing out of the surface. Negative flux means that E field's flowing into the surface. Something important to note, we're going to see this here in just a second, is that net flux is is ultimately talking about, you know, you're comparing how much of the field is entering the object that doesn't leave the object, or how much flux or how much field leaves the object that never enters, right? And we'll see that here in a second, but you'll notice that every line, every E field that enters the shape exits the shape as well in all of these cases. So the net flux would be 0 for all these cases. And we'll look at that more here actually on the next page. Okay. We're going to talk about something called a surface integral. Okay. And the surface integral is actually not that different than a regular integral. People freak out when they see surface integral, but it's really not that different than a regular integral. And it's actually, we can actually avoid doing calculus if we set it up correctly. In the above, so in the examples, the electric field in the uniform is surface and the surface are flat. However, you'll notice something like in this case right here, the light rays are not uniform. They're not going all in the same direction. So you'll notice that there is kind of a little changing orientation here as the light flows through the little sheet, okay? And then here you see that maybe we have like a Cheeto puff or something. The flux through it, the field lines are all uniform, but the surface is not flat. It's not, and so what you'll notice is that the orientation of the pieces and the A vector is going to change with respect to it. The way that we can find the total flux is to use an integral, okay? As you can imagine. There's 3 steps, and they're the same steps that we always use. Split surface, and this is very important to split the surface. We're not splitting the whole shape, just the surface, okay? Into tiny pieces dA, okay? Multiply, okay? To get the tiny flux, okay, d phi through each surface. Okay, so I could do d phi equals electric field dot dA. Okay. And then from there, I can just integrate to get the total flux. So then I would do add up all the tiny fluxes to get total flux phi. Okay. And so the equation I've already basically stated right here, d phi equals E dot dA. If you integrate both sides, you get phi equals integral E dot dA. Okay, so the way that this works is that the total flux equation just ends up being phi equals the integral of E dot dA. Okay, this is actually a surface integral. Okay, so we actually will note it with a little circle on the integral sign. That means it's a surface integral. Now, don't get tripped up because this is really just an integral with respect to the surface area instead of integrating through the entire shape. We've been doing integrals, with respect to everything, but now we just have to look at the surface. And this is actually an indicator that the problem can be really easy if you set it up properly, and we'll talk more about that in the next section. If you have a house made completely of glass, including the floor, is the net flux of light through the house positive, negative, or zero? Well, let's see. If you have the sun off to the side of the house, you're going to notice that everything that enters, okay, everything that enters goes out, okay? Every line that enters the house exits the house, okay? So that means you have just as much field going in as you have coming out, which means that the net flux on going in and the flux going out is the exact same. So it ends up being zero, okay? Because everything that goes in comes out, okay? The light bulb shining inside, well, notice that there's no E field going, or there's no light rays going into the house, but it's all coming out of the house. So it would have to be positive, okay? Light leaves, but never enters, okay? And then if the sun and the bulb are in place, well, we've already clarified that the sun the sun is going to shoot its rays through the house, and that is a net flux of zero, but the light bulb is going to emit its rays, going out of the house. Okay? And so you have the zero flux from the sun and then the positive flux from the light bulb. So this is still going to be positive, okay? Because the flux from the sun is equal to zero, but the flux from the bulb is equal to, it's going to be positive, okay? Okay. In the last diagram, the flux of light out of the house is only due to the light bulb, okay? If there were to be negative net flux in the first diagram, what would have to be added? Well, if we wanted to have negative net flux, we would need to have the light enter the house and never leave. So maybe we could put like a piece of paper or something to block the sunlight from leaving the house, okay? So maybe like something to catch the light. So I'm going to say something to catch the sunlight so it doesn't leave. Okay? So then you end up having more lines leaving the house, or then you end up having more lines entering the house than leaving. Okay? Okay. By the way, a closed surface is a surface that fully encloses a region of space. This goes in tandem with Gaussian surfaces, which is the big point of the next page, or the next section. So the biggest thing that's important is the net flux through a closed surface depends only on what's inside of the closed surface, because anything outside the closed surface doesn't contribute to the net flux, because everything that enters the surface is going to also exit. Example, here's your closed surface right here, okay? You have a closed surface, it's this little oval, okay? And you notice that every line that enters that surface, okay, also exits, okay? Do you see that? And that's because there's a charge on the outside of the surface. Everything goes in there. So here, you're going to see that your net flux is going to be equal to zero if you have something outside of it, okay? If you have, for example, another surface is this dotted line right here. you'll notice that you have more lines leaving the surface and you have nothing that enters. You have only lines that leave the surface, and you have nothing that enters. So the net flux would have to be positive. Okay. But remember and that's because the charge is inside the surface. Okay. If the charge was outside the surface, it'd have a net flux of 0. Okay. Do you see in this example down here? Okay, that you have, you have a one surface right here enclosing the negative charge, one surface over here enclosing the positive charge, and they're different sizes, which is fine. And then you have one big circle enclosing both the charges, like a big oval here that encloses both of the charges. Do you see that? Okay. Now, when you look at this, okay, you're going to see, okay, there's a lot more lines entering the surface. There's only lines entering the surface here. So my flux here is going to have to be negative. In the red one, it's positive. And you can also see that it's dependent on the enclosed charges. Okay? So another thing to consider too is that when you encircle both of the charges, the enclosed charge is 0 because you have a positive Q and a negative Q. The enclosed charge is 0. And therefore, there actually is no net flux. Okay? So we can say that down here, Q enclosed is equal to 0, so the flux must also be equal to 0. And that'll make more sense when we talk here about Gauss's law here at the bottom. Okay? The conceptual statement of Gauss's law says that the net flux of electric field through a closed surface is directly proportional to the net charge enclosed in the surface. Okay? So the more net charge that you have enclosed in the surface, the greater flux there is going to be. Okay? To give you the mathematical statement, this is on, I believe, if I'm not mistaken, this is on your formula sheet. The mathematical statement of this is the surface integral of E dot dA is equal to Q enclosed over epsilon naught. Okay? This is the easiest statement here, and because this actually is where the easy part comes in, because the surface integral, we don't even have to actually do any real calculus if we set this up correctly, and I'm going to show you how we set it up in the next section. Okay, this is the net charge enclosed by the surface. Okay, and then this is, of course, the permittivity of free space. Of free space. Okay. There are 3 tenets that we need to follow when we do Gauss's law. So when we pick Gauss's law, we're basically creating a surface around a charge or a group of charges or a conductor. Okay, and we are able to simplify the problem when we do that. Okay, so when we apply Gauss's law, we get to pick the shape. You can pick any shape you want, but there are shapes that are most appropriate. Okay, and it needs to fit these 3 tenets if we want to avoid actually doing calculus. Okay, and that's always what you should strive to do. You should always try to avoid doing calculus wherever possible. First thing is that the surface must obey the same symmetry as the charge distribution in the problem. Okay, typically this means if the conductor is a sphere, we pick a bigger sphere. Okay, if it's a wire, well, a wire is cylindrical, we pick a bigger cylinder. Okay, at every point on the surface, the E field strength is the same magnitude. Okay, and then at every point on the surface, the electric field vector is either tangent or perpendicular, okay, to the surface. So it's either parallel or perpendicular or normal to the surface. Okay, because If it's tangent, then the dot product would be equal to 0. If it's perpendicular, the dot product is going to be equal to 1. Okay? So then that makes your integral a lot easier because then you don't have to worry too much about it, right? Okay, I'm going to show you in the next part how we use Gauss's law to actually solve this stuff. So I'll catch you in the next one.